Welcome to this online tutorial on complex analysis. This video is suitable for students who are taking mathematics at the university level. So today we are going to discuss about, I've said that this video is suitable for students who are offering a course in university mathematics. We are going to look at Laurent Series expansion. Laurent Series expansion. Now, Laurent series expansion is an expansion which is common in complex analysis. A series representation of this form is a Laurent series expansion. A series representation of f of z equals summation from k equals infinity up to negative, from k equals negative infinity up to positive infinity, ak z minus z naught power k. A series representation of that form, we call it a Laurent series expansion. This is a Laurent series expansion of f of z about z equals z naught. Above z equals z naught. Now this expansion has two parts. We can break it down and we rewrite it as f of z equals summation from k equals 0 up to infinity ak z minus z naught power k, then plus summation from k equals 1 up to infinity negative k z minus z naught power negative k. I can rewrite this expansion as that. So we call this form. This one from k equals 0 up to infinity, we call this the regular part, the regular or analytic part of the expansion, and we call this the principal part, of the expansion. This is the regular part, in simple terms, the one without the negatives. This one. I can also write it as, let me start with this. If we substitute k equals 0, we shall have n naught, then k equals 1, n1, z minus z naught, plus a2 z minus z naught power 2 plus then plus this one from k equals 1 a negative 1 z minus z naught power 1. This is a negative, so we shall drop this thing down, then plus a negative 2 z minus z naught power 2 plus this part with fractions, we call it the principal part. Then the other one which has no fractions is the analytic part or the regular part. Now we are going to look at some examples. Examples on how to obtain such a series representation of a function. We are going to expand one. We are going to expand f of z equals 1 over z minus 1 into Laurent series valid. Laurent series valid for part A, valid for the following domains. Part A, the domain is this. Part B, we have z greater than 1. Part C, we have 0 less than z minus 1 less than 1. Then D, we have z minus 1 greater than 1. Z minus 1 greater than. We have those examples. Now, when you look at this question, you observe that f of z equals 1 z minus 1. F of z has singular points. It has singular points at z equals 0 and z equals 1. That is f of z. It has singular points. We obtain singular points by equating this denominator to 0. When we equate this denominator to 0, we shall obtain z equals 0 and z equals 1 as the singular points of that function. Now, such a function cannot have a Taylor series representation. Because of this those singularities. So for that case, we shall evoke the Laurent series representation if we want to expand such functions with singular points. We expand them about their points of singularities. So we are going to first break this down into a partial fraction. So we can let 1 over z minus 1 equivalent to a over z plus b over z minus 1. Try to do some algebra. 1 equals a z minus 1 plus b z. If z is 0, what shall we get? If z is 0, we shall get a as negative 1. If we substitute z equals 0, then if z is 1, we shall get we shall get b as 1. We shall get b as 1. So we can rewrite our function 1 over z minus 1 is equal to negative 1 over z then plus b 1 over z minus 1. So we are going to start with part A. So what do we know? We know that given a geometric series, we know what a geometric series represents. An infinite geometric series. This series A, let me say, we know that A over 1 minus R, this is equal to A plus AR plus AR squared plus sum to infinity of a geometric progression. We know that this converges for absolute R less than 1. That's what we know. The series representation of this form converges for that. So when you look at part A, we want something which will converge in this domain, absolute Z less than 1. That's why we need to use that knowledge of a geometric progression, sum to infinity of a geometric progression. So since we have our function f of z is now this. Let me start with this. In fact, most of the work is to deal with this function here. If we want to ascertain, a series representation in such a way that it is valid within this domain, we are going to do most of the work on this function. So what are we going to do now? We have 1 over z minus 1 over z minus 1. I can rewrite this as negative 1 over 1 minus z. Why am I rewriting it? I just want it to resemble this sum to infinity over GP. So this is going to be equal to negative. There is a negative outside. And if I'm substituting this, A equals 1, the first term, A equals 1, then the common ratio, you just compare. A is 1, common ratio R is Z. So we shall have this equal to 1 plus Z plus Z squared plus. And this is valid for absolute Z less than 1. It converges for absolute Z less than 1. Now we can substitute back. And we know that absolute Z is by the way positive. Absolute Z. So this is the same as it converges. We know that this is always positive. So it converges for that domain. That's why we needed to manipulate only this. Then get this, substitute it back, we shall get the required series representation. So f of z, which is negative 1 over z, then plus 1 over z minus 1. This becomes negative 1 over z, then plus, substitute this, this is equal to negative 1 plus z squared plus. I can open brackets. So we shall get this as f of z is equal to negative 1 over z minus 1 minus z to the 2, z to the 3 plus minus. This is valid for 0 less than absolute z less than 1. So that is part A. We are going to proceed with part B. Part B. Part B. Let me hope that you've taken note of this important question. Or I can maintain it. I can maintain it. That is part A. Then part B. Part B, where we want the series representation valid for absolute z greater than 1. So we have our function already. Our function already in partial fraction form. Plus 1 over minus 1. So we are going to break the other thing down. We are going to break this down to get the series representation valid for the required region. Take a note of the sum to infinity of a GP. It's very important in obtaining such a series representation. The sum to infinity of a GP. So we need to manipulate z minus 1, or 1 over z minus 1. This is the same as, I'm going to write it as 1 over z 1 minus 1 over z. So what have I done? I have factorized out z. Z is now factored out. Z is outside. Z is outside. So this is the same as 1 over z times 1 over 1 minus 1 over z. Now let me manipulate this using the knowledge of sum to infinity of a GP. 1 over 1 minus 1 over z. This is equal to, the common ratio now is this. The common ratio is this. First term, 1. So this is equal to 1 plus 1 over z plus 1 over z squared plus 1 over z to the 3 plus. And this is valid for absolute common ratio less than 1, absolute R less than 1. Our R is 1 over z less than 1. And this is the same as 1 over absolute z less than 1, which implies absolute z greater than 1. Greater than 1. So this converges for absolute z greater than 1. We can now substitute back 1 over z minus 1. 1 over z minus 1 is equal to 1 over z is equal to 1 over z. Then time was the expansion of this, which is 1 plus 1 over z plus 1 over z to the 2 plus. We can also open brackets. This is equal to 1 over z plus 1 over z squared plus 1 over z to the 3 plus. Substitute back. F of z now is equal to f of z, which originally was of this form, plus 1 over z minus 1. This is equal to negative 1 over z, then plus the expansion of this, which is 1 over z plus 1 over z squared plus 1 over z to the 3 plus. You can cancel out some terms which are common. this and this, negative and positive, they both cancel out. So f of z is equal to 1 over z squared plus 1 over z to the 3, 1 over z to the 4, plus. This is valid for absolute z greater than 1. Absolute z greater than 1. Absolute z greater than 1. So we are going to proceed with the next question. 1 over z squared plus 1 over z to the 3. Yeah. We're going to proceed to the next question. Part C. Let me hope you've taken note of part B. This is the solution to part B. Then C. We're going to proceed to part C. Part C, which requires us to obtain the series representation. But you need not forget how our function looks like. Our function is f of z equals negative 1 over z plus 1 over z minus 1. That is my function, negative 1 plus was it this? I think it was the one. I think it was the one. Maybe I can check. Confirm. Z minus 1. Then negative z plus 1. Plus z. Yes, that is it. This is our function. Part C requires us to obtain the series representation valid for this domain. Series representation valid for that domain. Now, when you look at that domain, I told you that we are obtaining these expansions about a point of singularity. When you observe this part A, we are obtaining the series representation about z equals 0. Part A, series representation about z equals 0. That can also help you appreciate the fact that we did not tamper with this, because this is already in the required form, as in it is already expanded about z equals 0. Yes, that's why we did not tamper with that form. So part A, we obtain the series representation about z equals 0. Part B, we also obtain the series representation about z equals 0. Now part C, when you look at C, we want to obtain the series representation about z equals 1. So what does it require? What are we going to do? What is required of us? That means we are not going to tamper with this form, this 1 over z minus 1, because it is already expanded about z equals 1. So we just need to make sure that this negative 1 over z is in that form, So what are we going to do now? What are we going to do? A moment. Let me first... moment. I think now I can use that. What does it require us to do? I can also get another marker. We want to obtain the series representation about z equals 1. So we are going to only deal with this alone. we are going to rewrite negative 1 over z. This is equal to negative 1 over z minus 1 plus 1. Since we want the series representation about z equals 1, you introduce a negative 1 and a 1 there. So this is the same as negative 1 over 1 plus z minus 1. 1 plus z minus 1. It's equal to that. Now recall that you need not forget this information. You shouldn't forget. Recall that a over 1 minus r is equal to a plus ar plus ar squared plus valid for absolute r less than 1. Absolute r less than 1. Now, since we know that, now what are we going to do next? We are going to expand this using this knowledge. So we have negative 1 over 1 plus z minus 1. I can write this as negative 1 over 1 minus 1 minus. I can leave the minus, I can leave it, yeah. I don't know why I'm tampering with it. We have that. So what is our common ratio in this case? Our common ratio is r is equal to, you just compare this with this. Look at the denominators. R is negative z minus 1. Negative z minus 1. Let me hope you agree with me that that is r, because I can write this as negative 1 over 1 minus negative z minus 1. So r is now this. R is that. There is a negative up. There is a negative up. So